Now let's start today's tutorial. So today is the last tutorial, so I will solve some questions which I already collect from somewhere. So today I will solve basically this question. So let's solve the first question. This question, let me take it. So so solve first question. So in this question it is asked that the average number of photon in equilibrium inside the cavity. So let's calculate that. So what we know about the photon, whenever we actually know the average number of, okay, so what we know about the photon, so we know basically about the photon is that we know that its average particle number in, if there are if there is a what it is called, there is the average particle number is 1 by e to the power beta epsilon minus mu minus 1. It is generally the occupancy number for any quantum particles which follow the Bose-Einstein statistics. So for any VE gas, so its occupancy number will be 1 by e to the 1 minus e minus mu. Since photon is a VE gas, then means for photon also we can write the occupancy number as follows. But inside a black body, here the cavity means inside a black body, we know that inside the black body always emit photon and also absorb the photon. So that means inside the black body the photon number is not constant. Means with the surroundings of this with this wall of the black body and the cavity, the photon is always allowed to exchange. The number of photon is spontaneously re-emit and absorbed by this wall. So that's why the total number of photon is not conserved inside a cavity. So that's why, since we know what we know, that since as we know what is the mu is the chemical potential as we know, but as like temperature, when we allowed to object exchange its energy, we know that both the objects average energy will become same, and this average energy or average kinetic energy is denoted by the quantity called temperature. Similar in case of chemical in case of when two systems are allowed to exchange particle among themselves, we will call that system is in equilibrium, or the system reached equilibrium if these two systems chemical potential became equal mu1 equal to mu2. But as for this inside the cavity of a black body, there is always emission and emission of photon and absorption of photon is always going on. So that's why this concept is not applied here. So for photon the mu is 0, chemical potential is 0. Now what is then the occupancy number? Now occupancy number is 1 by e to the power beta epsilon minus 1. So that we know, but here it is asked what is the average number of photon in the equilibrium state. Let's do it. So what will be then a total number of this is the number of particle sitting whose energy is equal to epsilon. But here it is asked ki what is the average number of energy, means inside this cavity there are lots of particles are there, or lots of energy state are there whose energy is not one particle value, but its energy, these photons can take energy between 0 to infinity. So let's do it. So let's write it. What is the relation between epsilon and what is the epsilon here? Or let me write it, epsilon. So beta epsilon, which is equivalent to, for photon, for single photon, if its frequency is nu, then energy will be, we know that, h nu, right? And what will be the total number of particle inside the volume 0 to infinity dx dy dz, and momentum 0 to infinity dpx dpy dpz. So any photons can be described by its three values of the momentum and three values of the position, so into the occupancy number by 1 by hq. Okay, now this simply give me the volume dx dy dz, total volume. Now we left with 0 to infinity dpx dpy dpz n. Now we know that this follows a spherical symmetry, and since the photons and two independent polarization state, so that means we have to also multiply with 2 by here. So 2 is denoted the degeneracy because of polarization, because of 2 independent polarization, okay. Now, so because of spherical symmetry we can write it like that, 0 to infinity 4 pi p square dp into n, and we know for a photon p is h nu by c, right, mc square by c. Okay. So momentum we know p equal to h nu by c. So what is the dp? dp will be hc by nu, so that means 8 pi v by h cube by h cube 0 to infinity hc its cube nu square t nu n. So 8 pi v c cube 0 to infinity t nu square, and let's put the value of occupancy number 1 by e to the power beta epsilon minus 1, and we know that epsilon equal to h nu, so put it there in place of epsilon, put h nu here. Now take h nu is equal to, take beta h nu equal to some variable x. Then what if we replace nu by x, we'll get 4 pi vc cube nu is equal to x by beta h, so 0 to infinity dx beta h x square beta square h square into 1 by e to the power x minus 1 8 pi v c cube 1 by beta cube h cube 0 to infinity dx x square e to the power x minus 1. So beta means we know that beta equal to 1 by kt, so 8 pi v cq hq. Beta means, that means kq tq, and this integration gives a constant number. Suppose this constant is alpha, so that means it's 4 pi v kq cq hq tq into some alpha. Now you can see from here that 4 pi kq cq hq, it proportional to v, volume of that cavity, and the temperature cube of the cavity. So from here we can say that the average number of photon in the equilibrium inside a cavity is alpha 8 pi kq cq hq v into tq, and it is straightforward from here that the total number of particle directly proportional to the volume of the cavity and also proportional to the cube of the temperature. So these two things is there. So that is that. So we have solved the first question. Now let's move toward the second question. Okay, in the second question we have to calculate the change in entropy in the free expansion. So let me first explain what the free expansion is. So free expansion means if we have a gas inside of box and it is connected something with a, okay, let it draw in this way. So suppose there is a box and this side is full of gas and this side is nothing. This is no gas molecule is there. That means it is a free space which is evacuated. That means there is no gas molecule at all and pressure is 0. So if I just remove this partition and let this gas molecule take this space, what will be the change of entropy, right? Since the pressure is 0, that means the gas will do no work. So that means from here since dW equal to the gas, dW equal to pdV, since the pressure is 0, that means the gas will do no work. Gas will do no work, and it is thermally isolated. That means no heat it cannot exchange heat with surroundings. So that means dQ also 0. So what is the change of the internal energy of the system? So from the first law of thermodynamics we know that dQ is equal to du plus pdv. So in this process, since the dW is 0, pdv is 0, dq also 0, that means internal energy or change in internal energy also 0. If the, since it is an, suppose we suppose that inside of this box there is a ideal gas molecule, ideal gas is there, and we know that for ideal gas temperature directly depend on the entropy on the internal energy of the system. If the internal energy does not change, that means if du is equal to 0, that means system's final and initial temperature are same. That means temperature, if temperature of this state is Ti, and in the next state, if the when the gas is inside everywhere, then it is Tf. Then since the internal energy does not change here, so that means Ti is equal to Tf. Now from here we can calculate one thing. So we know that the equation of PV equal to P initial V initial equal to N K T initial, and P final, it is the equation of state of the ideal gas, and PF VF is equal to NK TF. So from here we can calculate Pi Vi is equal to, since Ti equal to Fi, that means Pi Vi equal to Pf Vf, and suppose that this volume is V, these two volume is V, that means initial volume of the gas is V and the final volume will be V plus V 2V. So if I put it here, Pi into V and Pf into 2V, that means Pi by 2 is equal to Pf. So it tells us that the pressure will decrease by half, right? So this much we know. Now from the first law of thermodynamics, we know that TdS equal to du plus PdV, right? That means the change of here, obviously here this TdS, whenever I write, since dq is 0, here dq is 0 for this process where means there is no exchange of heat, but TdS means it is the heat required for the same process when you just go by this process reversibly. Then whatever amount of heat the exchange here, this, since this is a irreversible process, here it may happen so that the total heat exchange is 0, but whenever we write the TdS equal to du plus PdV, we write its process where if we just go to from this state to this state reversibly, we can go from this state to this state in many ways. One of the way is the free expansion, where we can see that it is a irreversible process and the dq is 0. But when we will write TdS equal to du plus PdV, then I am talking about that process where we taking from this state to this state via a reversible process, and in that reversible process it may happen that dq is not 0, dq may be there. So it is for a reversible, this part is for reversibly we are taking the system from here to here. And since SI, entropy, is a state dependent property, it does not depend on the which path I am taking, which path we are taking from here to here. It only depend on the final state and initial state. So that's why it does not depend on the path. It does not, since entropy we can write it, because entropy is a state dependent property. It will not depend on the path. Sorry, here entropy is not a state dependent. Here du, what I mean, du is a state dependent property. So the change in internal energy does not depend on in which path you take to just in which path the system goes from here to here. That means in this process also the du will remain 0. So in this process also du remains 0, since it is a state dependent property. Since it is state dependent, that means we know from here to here, from this state to this state, the change in internal energy is 0. So that means in this, when we just take the system in a reversible way, there also du will be 0, equal to plus p by t. I take t here, dv. Now initial to final ds, change in entropy, is equal to, since t also against a state dependent phenomena, since in ideal gas T and du are state dependent phenomena, so T will also remain same as the previous one, and we know that during the whole process T remain constant, so we can T is here also constant, so it will become P dV from initial to final state. Now we know that PV equal to RT. That means PV equal to RT. Here this is a constant, RT is constant, RT is constant, R is constant, and T also constant. That means dP VdP plus PdV plus VTP means PdV plus VdP is equal to 0. So we can write it PdV is equal to minus VdP. So here we can write it instead of, okay, one way we can write also, another way, okay, let me write it like this. Okay, let me write it like this: PV equal to, suppose, RT, then P is equal to RT by V, so 1 by T into V initial to V final, RT by V dV. Now this equal to TT cancel, so R V initial to V final dV by V, V final is 2V, so 2V, the final volume is 2V, initial volume is small v, so 2V to V dV by V, so this is equal to R ln 2V minus ln V, so this is equal to R ln 2. So from here you can see that the change in entropy delta S, or S final minus S initial, so from here you can see that S final minus S initial, the change in entropy equal to delta S equal to R ln 2. So we have calculated the change in entropy in the free expansion. So let's move towards the next question. So next question, okay, this question. Here it is asked that calculate the chemical potential for a classical one-dimensional oscillator. Let's do it. So whenever we have to calculate like this in statistical mechanics, we first have to calculate the partition function. For partition function, we need to write that what is the Hamiltonian. Here Hamiltonian is half p square by 2m, its kinetic energy, plus its potential energy, half m omega square x square, since it is one dimensional. Now what is its partition function? Since in classically this momentum and x are continuously varied, and also in classically the states are continuous, we can write the z as 1 by h square integration of dx integration of dp e to the power minus beta h. So it can be written as well 1 by h square dx dp e to the power minus p square minus beta p square by 2m minus beta by 2m omega square x square. So since we can write the integration of x and p separately, let's separate it out. Dx e to the power minus beta m omega square by 2 x square and integration dp e to the power minus beta p square by 2m. Okay, let's first do this integral first, then we will do this integral. So let do a separate assume that beta m omega square by 2 x square equal to y square. That means x will be 2 by beta m omega square to the power half into y, that is dx will become 2 by beta m omega square into dy. So if I put it here, this integration will become integration dy into root 2 beta m omega square, because dx, then e to the power minus this whole term is y square minus y square, this is minus infinity to plus infinity, so this integration become 2 by beta m omega square into minus infinity to plus infinity dy e to the power minus y square. And we know that the value of this integration is root pi, so that means 2 by beta m omega square into root pi. Now let's do this integration. To do this integration, we will replace this variable by another quantity. So beta p square by m, let's replace it by some number, suppose y square. So here p will be root over of 2m by beta y, that means dp equal to root 2m by beta dy. So if I put it there in this integration, it will become root over 2m by beta dy e to the power minus y square. So that means again minus infinity to plus infinity, so this will become root over 2m by beta integration minus infinity to plus infinity dy e to the power minus y square, and this integration again means root pi, so this will become root over 2m by beta into pi. So that means if we write the total things, it will look like 1 by h square into root over of 2 beta m omega square pi into 2 pi m beta. So this means, so m cancelled, beta 1 by beta this is h, not h square, this is h, this will be simply h. So since it is one dimension, so this is simply h. So 1 by h, 2 by omega. So this is beta means kt by h cut omega. So this is the partition function for single particle. So this is the partition function for a single particle. Now suppose that if we now in the system there is n number of particles, capital N number of particles, what will be the partition function? Since if there is a n number particle, then the Hamiltonian will become h equal to summation of I pi square by 2m plus half m omega square xi square. Now the partition function will become integration dpi I equal to, so it will become dp1 dp2 dot dpi up to dpn, since n number of particle is there, and similarly dx also dx1 dot dxn, and in e to the power summation of I equal to 1 to n minus beta, this quantity. Now here you can see that we can write, since these pi and xi are for every particle we can write the integration separately. That means we can write it like that: integration dp1 dx1 e to the power minus beta p1 square by 2m plus half m omega square x1 square. So we can write it like that into, for it is for particle number 1, then particle number 2 into particle number 3, and this integration from minus infinity to plus infinity, and we know from above that this integration is nothing but a constant which does not depend on the particle, which particle we are talking about. It will come kt by h cut omega. That means if we multiply n kt by h cut omega, that means the n total partition function for n number of particle will be z to the power n. Here is small z is the partition function for a single particle. So that means here we can write the partition function as kt by h cut omega to the power n. So then what will be the free energy? Free energy is nothing but minus kt ln z. So here minus n kt ln kt by h cut omega. And what will be its chemical potential? Mu equal to del f del n with all other variable remain constant, keeping constant. That means it will become minus kt ln kt by h cut omega, which is kt ln h cut omega by kt. I absorb this negative and just write it h cut omega by kt. So this is the chemical potential. This is the chemical potential for a classical one-dimensional oscillator at temperature T. So that's it. So we have solved this problem. Now let's solve another next question, which is similar, but in quantum, means if the oscillator is not classical but instead it is a quantum oscillator. Let's see it. So here this we want to calculate the chemical potential for one dimensional quantum oscillator. So let's do it. So for quantum oscillator we know that the Hamiltonian is H equal to n plus half ground state energy h cut omega. This is the Hamiltonian for a single particle. And this particle, the property of the particle is denoted by this omega. So single particle, what will be its partition function? Now here, since the system state is discrete, we don't want, means here the integration will not work, so we have to do summation over all the states. So summation over all the states n e to the power n equal to 0 to, so here is a n h cut omega, okay, summation, there is a, okay, so n equal to 0 to infinity. So yes, this is the single particle, this is the Hamiltonian for single particle whose frequency is omega and sitting at the state n. Now here you can, if you see that for a, we have write the e to the power minus beta h is the only energy for sitting in a particular state which is denoted by this p and x. If we change the p and x, the energy will change. So here also the particle are sitting with sitting in the n state, means its energy is n plus half h cut omega, but this n can take values 0 to infinity. So total partition function will be n plus half h cut omega. So this is in minus beta, so this is minus e to the plus e to the power minus beta h cut omega by 2 summation of n equal to 0 to infinity e to the power minus n beta h cut omega. So this is e to the power minus beta h cut omega by 2 into first n equal to 0 1 plus n equal to 1 e to the power minus beta h cut omega plus e to the power minus 2 beta h cut omega plus dot dot dot, and there is a this series sum has some value, since we know that 1 minus x to the power minus 1 is nothing but 1 plus x square plus x cube plus dot dot dot. So that means this series will become e to the power minus beta h cut omega by 2 into 1 by 1 minus e to the power minus beta h cut omega. So this series sums limiting value will be 1 by 1 minus e to the power minus beta h cut omega. So if we multiply above and below by e to the power beta h cut omega by 2, will get 1 by e to the power beta h cut omega by 2 minus e to the power minus beta h cut omega by 2. Now let multiply by 2 here and another 2 here. So this quantity we know as half by sine hyperbolic beta h omega by 2. So this is the partition function. Now as we know that from the this is the partition function for a single particle. Now the partition function for the n particle, similar as the previous one, we know that the partition function for the n particle will be, if the z is the single particle, then z to the power n, that means 1 by 2 sine hyperbolic beta h cut omega by 2 to the power n. So what will be the partition, its free energy will be kT ln z minus kT ln z, so which is minus kT ln means plus n ln 2 sine hyperbolic beta h cut omega by 2. Now what will be the chemical potential? Mu will be del F del N with all other things are constant, so that means chemical potential will be ln 2 sine hyperbolic, let it write as beta h cut omega by 2 kT. So it will look like that. Now if you want to compare with this, so there will be some kT will be also there, so kT is there. So now we want to what, we want to compare it with, we compare it with this classical counterpart. So this is the chemical potential. Now we want to compare with it classical counterpart. So kT ln 2 plus ln e to the power beta h, okay, let it write beta h cut omega by 2 minus e to the minus beta h cut omega by 2 by 2. So these two cancel, so it will look like equal to kT ln e to the power beta h cut omega by 2 minus e to the minus beta h cut omega by 2. So if I take e to the power ln, we take common e to the power beta h cut omega by 2, it will 1 minus e to the power minus beta h cut omega. So that means kT ln e to the power beta h cut omega by 2 plus kT ln 1 minus e to the power minus beta h cut omega. Now it is kT into beta h cut omega plus by 2 kT ln 1 minus e to the power beta h cut omega. So h cut omega by 2 plus kT ln 1 minus. So it is means I have thought that it will come in this form, but it is not actually coming in this form. What it comes that here some per particle free energy is there. So per particle free energy, in per particle free energy, first term is for the ground state energy. What is the ground state? This is the ground state energy. You know that there is the ground state energy. So that ground state energy is there, and then basically something is there. So this is the chemical potential for the one dimensional quantum oscillator at temperature T. Now let's move toward the next question. Okay, entropy. Okay, this is a nice question. So here it is asked the entropy of a simple harmonic oscillator SHO whose has energy this. So it means P square by 2m plus half m omega square x square equal to energy E. That means to calculate the entropy we need the since microstate, total number of microstate. So let's calculate that. dp dx into delta p square by 2m plus square x square minus c. And what is this? This is nothing but the, if you can draw it, if you can draw these things, so it will look like p square by 2me plus x square by 2e by m omega square equal to 1. So it is a ellipse. Basically at the boundary it is always followed that at the boundary every so every point will follow, every point, total number of microstate, every point will follow this equation, p square by 2me plus x square by 2e by m over square. So integration dp dx, that it will be what is the length of this periphery, or what is the circumstances of this ellipse. It will be approximately equal to 1 by h pi, if this is b and this is a, so this will become a plus b. And what is a here? A here root over 2 me. And what is b here? A is this, b is root over 2e by m omega square. So total number of microstate will be 1 by h into pi root over of 2e by m omega square root over 2me. So it is 1 by h into, if I take common root over, so this is that, pi by h root 2e by m omega square plus root me. So what is the entropy? Then entropy will be k ln omega, which is k ln pi by h into this quantity, but 2e by m omega square plus root 2 me. So this is the entropy if the system possesses some fixed energy E. So that's it. So we have solved this question. Now move toward the next question. So this will be the last question for this tutorial. Question 11. Here it is asked that for a spin half system, magnetic momentum mu placed in a magnetic field H, what is the specific heat? Right. So we know that we have to write the Hamiltonian. So what it will be the Hamiltonian for this? H will be, what is the number of particles which are in the upward direction? Its energy will be mu h. And what is the energy of the particle which is downward? Their energy will be mu h. Okay, let me write it in this way. Okay, so its Hamiltonian is basically mu dot h, mu dot, okay, let call this magnetic field B. So mu dot B is the Hamiltonian. So what will be the partition function? Partition function will be the all possible combination of energies e to the power all possible direction of mu e to the power minus beta mu dot p. And since we know that it is a spin half system. That means it's only two energies possible. One is one when mu and b are the direction of the mu and b are same, then it will be mu b. When its direction will be opposite, it will be minus mu b. So that means this summation will give us minus mu b plus e to the power plus beta mu b, which is 2 sine hyperbolic beta mu b. Now this is for a single particle. Now for n particle, as we know, for n particle the partition function will be z equal to z to the power n, which is 2 to the power n sine hyperbolic n beta mu b. And what will be its average energy? Average energy will be minus del beta of z. This will be its part. Okay, so sorry, so the average energy will be minus del beta of ln z, which is minus, so if I take ln z, so let first ln z will be n ln 2 plus ln sine hyperbolic beta mu b. This is the thing. So first term will, there is no dependence of beta, only the second terms will remain. So minus n ln sine means 1 by sine hyperbolic beta mu b cos hyperbolic mu b. This will be minus n cot hyperbolic beta mu. Okay, let me see it. Okay, it is not sine, actually it is actually cos. So plus sign is there, so it is cos, so not sine, cos hyperbolic. So this is cos hyperbolic, cos hyperbolic. This also cos hyperbolic, cos hyperbolic. So then the integration will become, this will be cos hyperbolic beta mu b, and upper part will be sine hyperbolic, sine hyperbolic, sine. And the derivative cos hyperbolic means e to the power mu b plus e to the power minus mu b. Okay, so derivative will be plus and when you just derivative, then here one thing is with respect to beta, this quantity will came up mu b. So this is basically average energy will be in mu b tan hyperbolic beta mu b. So this will be the, so this negative sign should not be there, so somewhere this negative sign should absorb. So n mu b tan hyperbolic beta mu b. Now what is the specific heat? C is equal to del E del T, and we know that beta equal to 1 by, suppose let beta equal to 1 by T, then del, so okay, beta equal to 1 by T, so let it there. First n mu b del T of tan hyperbolic, I think negative sign is there, actually negative sign is there, negative sign is not is there, not absorbed by anything, it is there. tan hyperbolic mu b by kt, beta equal to kt. So now n mu p, tan hyperbolics, if a derivative it will become sec square hyperbolic mu b by kt, and what remain will be with respect to t, so minus, a minus sign is already there because of e, minus mu b by k t square, right, del t t square. So this will absorb here, so it is look like n mu square b square k t square sec square hyperbolic mu b by kt. So this will be its specific heat. So that's it. So that's the end of my today's tutorial. So there is no particular question in my mind, so that's it. Okay, if you have any question in your mind, you can ask me, or I can leave this meeting right now. Okay, I will end this meeting.